I'm going to just briefly introduce, and then of course Sushmita or either Dibanjali is going to take over and do the formal introduction. So first of all, thank you all for joining us today as part of the ECS Purdue chapter webinar series. And our webinar series is particularly on women in electrochemical sciences and engineering. And we're very pleased to have Professor Nav Nidhi Rajput from Stony Brook University, Department of Material Science and Chemical Engineering. On a personal anecdote, Professor Rajput and you also can see Professor Vilas Paul from Chemical Engineering Purdue Online. We certainly, I think, have collaboration things that we're trying. So very recently, I think, again, thanks to Professor Rajput for leading such proposal development, I think. so that was a recent one we tried to work on. So with that, I will like to say a big vote of thanks to Professor Rajput for accepting the invitation and speaking here today. With that, let me hand it over to either Dibanjali or Sushmita. One of you is going to introduce. And Dibanjali is the communications director of the chapter, and Sushmita is online. Sushmita is the president of the chapter. So I think one of them is going to introduce you formally. So thank you, and thank you all.
Thank you so much, Partha, for inviting me, and a very kind introduction. Yeah, thank you so much.
Thank you so much, Professor Mukherjee. So I welcome you all to today's talk as part of our spring webinar series. For those of you who are new here, the ECS student chapter at Purdue is led by our chapter officers under the guidance of faculty advisors, Professor Partha Mukherjee and Professor Julia Laskin. So last semester, we organized the Fall 2020 webinar series with talks by a host of eminent speakers, and that was very well received in the scientific community. So this semester, we are back with our webinar series on women in electrochemical sciences and engineering. Tune in every Monday to listen to a stellar cast of women researchers presenting their work, thoughts, and reflections from their scientific journey. So as part of this webinar series today, we have Professor Nav Nidhi Rajput from Stony Brook University, who will be talking about material informatics for next generation batteries. A short introduction about Professor Rajput. She received her MS and PhD degrees in chemical engineering at Louisiana State University, specializing in molecular dynamic studies of ionic liquids confined inside nanoporous materials for applications in electrochemistry. She worked as a postdoctoral research associate in the Energy Technologies Area Division at Lawrence Berkeley National Lab, California, where she worked on developing infrastructure for high-throughput computations for the Joint Center for Energy Storage and Electrolyte Genome, which is a coupled first principle and classical molecular dynamics code base for rapid understanding and design of optimal electrolytes. Her research group at Stony Brook University seeks to use materials informatics to understand and predict the properties of fluids and solid fluid interfaces by gaining a fundamental understanding of synthesis structure property relationships. Professor Rajput, thank you for being with us today, and I hand it over to you for your talk.
Thanks, Dibanjali. Okay. I'm not sure if my screen is still shared. I guess I need to reshare.
Yeah, you need to share it again. Sorry.
Yeah. No worries.
Thank you.
Okay. Perfect. Can you see my screen?
It shows a little white screen right now.
White blank.
Yeah.
Oh, really? Okay. How about now?
Yeah.
Perfect.
Okay, perfect.
Yeah, you need to just do it that full screen mode, I guess. Yeah.
Yeah. Okay. Okay, is it good?
Excellent, thank you.
Okay, so let's get started, and thank you everyone for your patience despite being all the technical glitches. I'm glad we are able to get started. Thank you so much, Partha, for inviting me over, and thanks Devalina and Sushmita for taking care of all the logistics. It's really a pleasure and honor to be a part of this webinar series for women in electrochemical sciences and engineering. So today I'm going to talk about my work, which is focused on using materials informatics for developing next generation energy storage devices. And I'll be talking about how we are using these powerful computational tools to create a more energy efficient world. And let me start by giving you a brief idea of why and how urgent it is to start utilizing the power of electricity and explore sustainable clean energy sources. So as I'm sure everyone here must be familiar about global warming. And if you search online about global warming data, this is probably the first few links that you would find online, which shows that we are emitting greenhouse gases at a very alarming rate. Does anyone have any idea of how the amount of gases we are emitting every 24 hours in our atmosphere? A ballpark number? Anyone from the students? Okay, tough question. Yeah, but I can answer it for you. So we are spewing almost 110 million tons of heat trapping gases every 24 hours in our atmosphere. And that's a very alarming number. And these gases are rapidly increasing Earth's average surface temperature, resulting in extreme weather conditions such as high intensity and frequency of droughts, snowstorms, floods, and other disasters. And unfortunately, these disasters are not only costing us billions of dollars, but also several hundreds and thousands of lives each year. Okay? And there are many sources to these greenhouse gases. But the heart of the problem is that we still rely on dirty carbon-based fuels for almost 80% of all the energy that we generate every year. And on the right-hand side, you're looking at the energy consumption chart. And you can see here that there are three main sectors: electricity grid, transportation, and industry, which consumes 90% of all the energy that we generate every year. So you can imagine that if we can transform these three sectors, we can significantly reduce greenhouse gases emissions, right? So the transformation in the transportation sector requires replacing gasoline with electricity, for which we need better electric vehicles. And to have better electric vehicles, we need better energy storage devices. For the electricity grid sector, our society is already moving toward clean energy sources such as wind and solar. And they're great, they're getting cheaper and cheaper, right? But the problem with them is that they're intermittent sources, right? We don't have any wind on a calm day, and there's definitely no sun at night. So even if we are generating, say, 30% of our electricity from wind and solar, if we don't store it in some sort of energy storage device, so we really end up wasting all that energy. So again, for grid, we need better energy storage devices. And at the same time, if we can integrate the energy generated from wind and solar with chemical manufacturing through a large-scale implementation of electrosynthesis process, that can result in electrification of chemical industries. So our group is using computational tools to design materials to target these three sectors. But in today's talk, I'm going to focus on the energy storage devices work in our group. And when we talk about energy storage devices, the first name that comes to our mind is lithium-ion batteries. And I'm sure each one of you must be carrying a lithium-ion battery in your pocket right now. You're all using it, using your laptops, right? And they deserve all the attention because they're currently the best technology in market out there. And they're used in all electronic devices.
Are we pretty much set with everything else then? Do you have all the like the support staff for running Zoom meetings in case anything goes wrong?
And I think there's someone. I think someone has a microphone unmuted. Hello?
Yeah, I think you're good to go. I think.
Okay.
Yeah.
Thanks, Partha.
Professor Nidhi, like I think yours is showing low battery on your Mac.
No.
Okay, I'm coming to that, Sushmita. Yes, my laptop is showing low battery. Okay, thanks for letting me know. So I was talking about lithium-ion batteries, right? And I was saying how they are the best technology in market out there, and they are also used in some of the newest electric vehicles, such as Tesla and Nissan Leaf. But despite all these advantages, lithium-ion batteries are predicted to be incapable of meeting the future energy demand. Okay. And I'm sure everyone must be familiar with this message at the top. and the anxiety that we all experience when we are giving an important presentation and we run out of battery, right? And it's not just the inconvenience, but there are also several dangers associated with it, which you might have heard or experienced when your batteries are getting hot and catching fire. And that's a big warning sign for their use in electric vehicles. Okay. Another problem is that they're pretty expensive, which makes the electric vehicles expensive. So if we really want all of us to drive around in a Tesla car, we need batteries with much better performance, better safety, and at lower cost. And we are trying to achieve that goal by exploring this beyond lithium-ion battery space. And ideally, you would want to be on this upper right corner of this Ragon plot with something that has very high energy density as well as power density. Okay. And like any other researcher, when we started this work, we did our homework. We learned that this beyond lithium-ion battery space is large. It's unexplored and it's very rich with several chemistries that needs to be explored, thousands of known materials that needs to be explored, and millions of unknown materials that can be explored. So it's a huge chemical and parameter space. And if we go with the traditional trial and error based approach of testing each and everything in the lab, it's nearly impossible to find the next best material. Okay. To overcome that problem, we use the Hollywood approach. So if there are any Iron Man fans in the audience and remember the scene from the movie, so here basically the Iron Man is asking his computer Jarvis to scan the entire periodic table, and that's how they discovered a new element called vibranium for the arc reactor, which is not a real element, by the way, but our approach is similar, to use powerful computers to scan to a large chemical space and find the best optimal material for the given application. Okay. So my lab is using a computational infrastructure for high throughput multi-scale simulations. And there are two keywords here. High throughput means instead of running each calculation at a time, we have automated everything and we can run hundreds of calculations simultaneously. And multi-scale means we are doing simulations at different length and time scales, so we can study properties over a wide length and time scale. Okay. So we start with the database of material, and we perform quantum mechanics calculations to study electronic properties of materials, such as their electronic structure, their stability, reaction rates, and so on. We then use these quantum mechanics calculations to develop force field parameters. Okay. And you can think of these force field parameters as like some empirical correlations, which tells you how a bond is stretching or an angle is bending in a molecule. And we then use these parameters to perform classical molecular dynamics simulations in which we can study many body properties of materials. For example, what's the solvation structure, what's the viscosity of a solution, what's the conductivity, along with some other properties. And in this feedback loop, we then take information from classical molecular dynamics and feed it back to quantum mechanics calculation to get a better estimate of the energetics and also to analyze spectroscopic signatures of different stable species in the solution. And throughout this process, we are developing computational databases, which are then used to train machine learning models. And this entire infrastructure is built upon existing code bases in the materials community, where we are using PyMedGen to create the input file and parse back the output file. We have a code base called Custodian, which acts as an error handler. So if something goes wrong in our simulations, it tweaks the input file and resubmit the jobs in the workflow so that we have as little manual interference as possible. And we have another code base called Fireworks, which is primarily used for workflow development and management. Okay. And a general screening strategy we use here is to down select a pool of candidates based on property evaluation. So starting with the database of materials, we perform these high throughput multi-scale simulations. And as the molecules pass through each tier, Those who meet the selection criteria of that particular tier are then permeated down to the next level for further evaluation. And once we have a smaller pool of candidates, we suggest those to experimentalists for validation and testing. Okay, so let's get started with Energy Storage 101, which I'm guessing most of you must have either studied in a course that you might have taken. And there are primarily 4 ways of storing energy in a material, right? The simplest thing you can do is take an electrode, immerse it in an electrolyte, and by doing that, you form a double layer capacitor in which you are reversibly adsorbing and dissolving ions at the surface to store charge. It's simply a physical adsorption and desorption, so this process is very fast and you can do it thousands of times. But we are limited by the surface area of the material on which we are storing the charge. So the amount of charge that can be stored is very limited. If you want to utilize the bulk storage of the electrode, you can take a layered material and you can move ions into the lattice and push them. And that's called intercalation. That's what we use in lithium-ion batteries. And now by utilizing this bulk storage, you can store a lot more charge. The cycle life, the number of times you can charge and discharge a battery is also pretty high. But you can imagine that if you try, we still have limited lattice sites. And if you try to push more, volume can expand and other bad things can happen to this battery. Another thing we can do is something called deposition dissolution. And you can think of it as lithium or copper ions comes in and plates on the surface. And now we are storing energy using high energy chemical reactions. So the amount of energy stored is very high. But unfortunately, every time we charge and discharge a battery, we are in a way messing up with the morphology of the electrode, due to which the cycle life is very limited. And if you're tired with all the problems related to electrodes, you can store energy in electrolytes. And that's the concept of redox flow battery, in which you store a catholyte and an anolyte in 2 separate tanks. You react these liquids to store energy, okay? And all these different storage mechanisms are limited by basically inherent problems related to the electrodes and electrolytes. And our lab is focused on designing novel optimal materials for this different energy storage mechanism. And in today's talk, I'll focus on 2 stories, intercalation and deposition dissolution mechanism. Okay, so let's get started and see how we can use the intercalation mechanisms to store more energy compared to lithium-ion batteries. Okay. And before that, let's take a step back and see how lithium-ion batteries work. And like any other battery, it consists of a positive and the negative electrode, the cathode and the anode, and the battery is filled with this transport medium, the electrolyte. And when you discharge a battery, the lithium ions start migrating from the anode side, traveling through the electrolyte, and they intercalate into the cathode. And the exact reverse process takes place when we are charging the battery. I would like you to remember 2 things here. One is, when the ions are in the solution, they are surrounded by the anions and solvent molecules, which forms this solvation sphere around cation. And I'll be talking a lot about these solvation spheres and how it affects the performance of battery. The second thing I would like you to remember here is the formation of the solid electrolyte interface, which we form due to decomposition of the electrolyte species at the interface. And in lithium-ion batteries, this SEI layer acts as a protective layer. It protects the anode, but at the same time, it allows conduction of lithium ions, okay? So one way to achieve performance beyond than what is offered by lithium-ion batteries is to replace these monovalent lithium ions with multivalent ions such as magnesium, zinc, and calcium. And by doing that, we can store much higher volumetric capacity. Most of these chemistries are known to be not plagued by dendrite growth, which is one of the main reasons why lithium-ion batteries catch fire. And they're known to be safer than lithium when exposed to air. And all these chemistries have their own advantages and disadvantages. But in particular, magnesium ion batteries have gained a lot of attention over the past several years because of their high capacity, high voltage, and significantly lower cost. However, successful commercialization of magnesium ion batteries have several challenges. One of the major problem is something called passivation layer formation. So if you remember in the previous slide, I told you that in lithium ion batteries, the SEI layer allows conduction of lithium ions. Well, that does not happen in magnesium ion batteries. And we form this truly impermeable blocking layer, which does not allow conduction of magnesium ions. Another problem with magnesium batteries is the slow diffusion of ions in the electrode because of their divalent nature. So if you want to basically commercialize magnesium ion batteries, we need electrolytes with high ionic conductivity, wide electrochemical stability window, and chemical compatibility with both the electrode materials. So pretty much everything that you can expect from an electrolyte. And in the search of these electrolyte, we begin our study with a very simple magnesium salt, magnesium with TFSI anion and Diglyme solvent molecule. And in this work, we combined experiments and simulations to basically zoom into the solvation structure around magnesium. And we learned that magnesium is six-fold coordinated by the oxygen atoms of this TFSI anion, as well as the Diglyme solvent molecule. And it does that in a way that it forms contact ion pairs, even at very moderate concentration of 0.4 molar. And here is the definition of ion pairing that we used, that if the coordination number between cation and anion is 0, we define them as free ions. Between 0 to 1, they are defined as solvent separated ion pairs. 1 to 2 contact ion pairs, and more than 2, we call them aggregates. Okay, so this information that magnesium TFSI Diglyme solution forms ion pair even at 0.4 molar was very new and different than what was reported before for lithium ion electrolytes, where we do not see any ion pair formation even up until 1 molar concentration. So to further investigate this degree of ion pair formation, we prepared an electrolyte matrix with different anions and different solvent molecules. And we considered solvents with a range of dielectric constant, as well as some linear and cyclic geometries. Okay. And we looked at the coordination number of the cation and solvent and cation and anion to get an estimate of the solvation structure here. So for better solvation, you would want to have higher coordination number of magnesium solvent and lower coordination number of magnesium and anion. And we learned that pretty much all of these magnesium salts have a very strong tendency to form either ion pairs or aggregates in the solution. Some of the high dielectric constant solvents like DMSO, they provide very strong solvation and can separate magnesium from the anion because they bind with this polarizable oxygen atom. On the other hand, other high dielectric constant solvents such as acetonitrile fail to do so and result in formation of aggregates. An interesting trend was observed here for glymes, which show very low dielectric constant of 7, but they have the ability to basically wrap around magnesium ions, and they have high oxygen donor density, due to which they are able to basically dissociate magnesium from the anion. And for the anions, we found a trend that if you have a bulkier anion like TFSI, it has a lesser degree of ion pair formation compared to the smaller molecules like BF4 and BH4. Okay, lots going on here, but the take-home message from these results is that solvation is a very complicated phenomena, and unlike the common notion that it depends only on the dielectric constant, it also depends on other factors such as donor number and the geometry of the anions and solvent molecules. Okay, and this work basically improved our understanding of what's happening in magnesium ion batteries and how it's different than lithium ion batteries. In lithium ion batteries, if you want to deliver this lithium to the surface, you need to just strip away these solvent molecules. But in magnesium ion batteries, due to high tendency of this ion pair formation, it's actually the anion which delivers magnesium to the surface during the charge transfer process. And with this understanding, it became important for us to study if the anion remains stable during this process or not. So to test the stability of anion, we computed the bond dissociation energy of this TFSI anion, which is a measure of chemical stability of a molecule. And we tested the stability in 3 different medium: the anion by itself, the case when an ion is paired with magnesium 2+, and the case when an ion is paired with this reduced transient magnesium 1+. And different bars here represent different bonds of this TFSI anion. And we observed the anion is pretty stable by itself. That's expected, right? And it's also stable when it's paired with magnesium 2+. But this carbon-sulfur bond becomes unstable when the anion is paired with this reduced transient magnesium 1+. So what's happening here is that during the charge transfer process, this ion pair undergoes a partial reduction by taking an electron possibly from the electrode, and this process activates the anion and make it susceptible to decomposition. And that's pretty bad for our battery because we are not just losing the active species, but we are also depositing a layer of this decomposed product from the anions, which forms this blocking layer and does not allow conduction of magnesium ions. So this fundamental difference between lithium and magnesium, this multi-electron process, puts a severe penalty on the stability of delivery vehicles here, which in this case are the anions and not the solvent molecules. And our experimental collaborators at Sandia National Lab were able to validate this TFSI breakdown mechanism, where they found some TFSI decomposed product on the electrode during cycling, which is an indication that TFSI is breaking down. And they also observed some fluorine cluster in the solution, which shows that we are breaking this carbon-sulfur bond and which is liberating fluorine in the solution, as was predicted by simulations. So our solution to this problem was simple. Well, the ion pair formation is causing the problem, so let's just get rid of it, okay? So computationally, we screened a range of concentration where we are not forming ion pairs, okay? And we gave that to the experimental collaborators. They were very nice, so they tested everything for us. And they came back to us with these results, which shows that the electrochemical performance at very low concentration, where we claim that there are no ion pairs, is even worse. Okay, the performance actually deteriorates instead of improving. And we were wondering, why don't the low concentration work better? Okay, and that's a classic example of why experimentalists don't trust computational people. But we were surprised that why don't these low concentration work better, because definitely at low concentration, there is no cation and ion pair formation. And that brought our attention to the solvent, to what's happening to the solvent at these low concentration. And we identified that at very low concentration, it's the solvent which is completely surrounding the cation, okay, and forming a very strong bonding. So we tested the chemical stability of the solvent. Again, we did it in 3 different chemical environments: the solvent by itself, solvent when paired with magnesium 2+, and the case when solvent is paired with magnesium 1+. And the solvent is pretty stable. It becomes actually more stable when paired with magnesium 2+. But you can see that pretty much all the bonds turn from being highly endothermic to highly exothermic when the solvent is paired with magnesium 1+. So what's happening here is that at very low concentration, when it's only the solvent that's binding with the cation, during the charge transfer process, because of this partial reduction, the solvent becomes highly unstable, and that results in decomposition of the solvent and an even worse layer at the interface compared to what we were forming with the anion decomposition. Okay, I'm not sure if I was able to motivate the audience so far to pursue magnesium batteries, because so far I just told you how the anion breaks down and how the solvent breaks down. But what's important here is how we used this knowledge to design improved electrolytes. Well, TFSI is a very interesting anion and has lots of good properties, but we learned that it breaks down by breaking this carbon-sulfur bond. So we wanted to eliminate that possibility. So we replaced the sulfur with either phosphorus and silicon. We attached different functional groups to this molecule and derived 15 new molecules from this base anion. We then tested them for their electrochemical stability by giving an electron to the molecule and taking away an electron and ensuring that they're stable up to 4 volt. So from 15, we screened down to 6 stable molecules. We then tested them for their chemical stability, again by breaking each bond in different chemical environment and ensuring that they remain stable. So out of 15, we screened down to 5. And then finally, we tested them for hydrolysis, because water can be present as an impurity and can lead to decomposition of the anions. And finally, we were able to screen 4 promising anions with much better electrochemical and chemical stability and lesser degree of forming ion pairs with magnesium ions. Okay. However, we understand that computationally derived new molecules are not always the best molecules for synthesis, and it's not always possible to synthesize these completely new molecules. So we also tried to enhance the performance of existing magnesium electrolytes, and we studied the effect of ligand in magnesium borohydride salts. And here we considered a magnesium borohydride salt with Glyme solvents, and we increased the chain length of Glymes from DME, which has 2 oxygen atoms, all the way to tetraglyme, which has 5 oxygen atoms. Okay. And we learned that as we are increasing the chain length of Glymes, there is an increase in the magnesium solvent interaction. And this increase in magnesium solvent interaction results in a decrease of magnesium cation interaction, magnesium anion interaction, where the coordination number of magnesium and anion decreases from the range of being in aggregates all the way up to solvent separated ion pairs. And the effect of this change in solvation structure was observed on the electrochemical performance, where we found that there is a monotonic increase in the Coulombic efficiency as we are increasing the chain length of Glymes. Okay. So by just simply increasing the oxygen tonicity of solvents, we were able to enhance the electrochemical performance of magnesium salts. Another simple strategy we adopted was to mix competing salt. And here we added magnesium TFSI with magnesium borohydride salt in a Diglyme solvent. Okay, and the purpose was to let these 2 anions compete with each other to bind with magnesium. So computationally, we screened a series of different ratio of these 2 salts to find the ratio where neither of these salts are forming contact ion pairs, and the coordination number of both magnesium borohydride as well as TFSI is on an average less than 1. And in this competition of this TFSI and borohydride anion to bind with magnesium, it's actually the solvent who wins, and the coordination of magnesium and solvent increases. And our experimental collaborator tested this, and they found that indeed at this particular ratio, the electrochemical performance is the best. And we identified that we are forming several stable structures in the solution, where we have both the TFSI as well as the borohydride anion in the first solvation shell in such a way that it increases the stability of the anions as well as the solvent molecule. So by using this simple strategy of mixing competing salts, we were able to reduce the cation and ion interaction, which enhances the electrochemical performance of magnesium electrolytes. So in conclusion of the first story, I hope I was able to give you some idea of how we first learned why magnesium batteries don't work. And then we used that knowledge to design completely new electrolytes, as well as we enhance the performance of some of the existing magnesium salts. Okay. Okay, so let's move on to the next story of today's talk, which is on lithium sulfur batteries. Okay. And lithium sulfur batteries are really considered as the next generation batteries for electric vehicles. And the reason is right here. They have the capability of providing almost 5 times higher energy density compared to lithium ion batteries. And here is the current performance, current energy density from Tesla motors, and this is the one projected for lithium sulfur. They can also be significantly smaller and lighter than lithium ion batteries, and much cheaper than lithium ion because of high abundance of sulfur in earth crust. And these batteries are not new. There is more than 4 decades of research going on in this area. But unfortunately, lithium sulfur batteries still suffer from short cycle life, low charging efficiency, and poor safety. And that mainly happens because of the dissolution of lithium polysulfide species into the electrolyte, which limits the cycle life of lithium sulfur batteries. And I'll explain in a minute what I mean by that. For that, we need to understand the chemical process in lithium sulfur batteries, which includes basically dissolution of lithium metal into this alkali metal lithium polysulfide salt, where lithium reacts with sulfur to form Li2S8. As the discharge progresses, more and more lithium comes in, and we are forming a variety of different lithium polysulfide species such as S6, S4, and so on, all the way up to solid Li2S. And the reverse series of reactions takes place during the charging process. So far, so good. Nothing's wrong with these batteries. The problem arises when a lot of these lithium polysulfide species, along with some radical anions, start migrating toward the lithium metal side, and they result in parasitic reaction at the interface and in the electrolyte, and which is called the redox shuttle phenomenon. And this process takes place every time we are charging the battery. So we ultimately end up consuming the active sulfur species, and we are also corroding the lithium metal anode, which reduces the charge discharge capacity. And most of the effort in literature is focused on somehow suppressing these polysulfide species toward the cathode side by either using membranes or coating and porous materials, which have been successful as well. But at the same time, any additional material in lithium sulfur batteries further affects and impacts the much needed charge discharge capacity. So our approach is a little different. We are trying to design optimal electrolytes which can resist the dissolution of polysulfide species and hence suppress this redox shuttle phenomenon. So for this computational work, like I said, there's a 4 decades of research going on in this area. We started with the systems which are known to work and tried to get a better understanding of that. Okay. So here you are looking at the first discharge and charge cycle for the charge curve of the first cycle in lithium sulfur battery. And this can be divided into different regions. The first region is where elemental sulfur react with lithium to form Li2S8. And the second region is where we form a bunch of different lithium polysulfide species. I would like you to notice here that there is a sharp voltage decline in the second region. And I'll talk about that in a minute of why we think that there is the sharp voltage decline in the second phase. Okay. Another thing to note here is that the Gibbs free energy of these different lithium polysulfide species is very close to each other. And that's why they basically coexist in the solution through a series of chemical equilibrium. So in our work, we considered lithium polysulfide species all the way from Li2S2 to Li2S8. The choice of salt is very crucial for lithium sulfur batteries, and most of the traditional salts like BF6, BF4, BOB are known to be not compatible with polysulfide and solvent. And the state-of-the-art salt is 1 molar LiTFSI, which was used in this work. Similar to salt, the choice of solvent is also very important, and several traditional esters, carbonates, phosphates, which are known to work in lithium-ion batteries, they don't work in lithium sulfur batteries. And there are a handful of solvents which are known to work, and we considered most of them in this work. Okay. And we started this study by looking at how lithium polysulfide intermediate interact with solvents and lithium salts. So first system we studied was Li2S2 in an equimolar mixture of DOL and DME solvent. Okay, and here you are looking at the solvation structure of the system, where we observe that we have a very strong interaction between lithium and S2, and a very, very weak interaction between lithium and solvent molecule. Now, the weak interaction between lithium and solvent could be coming from either the low dielectric constant solvent of these two solvents, which is approximately 7, or it can be coming from a very strong interaction between lithium and polysulfide. And then when we looked at the solvation structure of lithium-lithium, we observed this very well-defined long-range structure, which is an indication of these polymeric species forming in the solution, where sulfur basically acts as a bridge between different lithium ions, and we form this lithium-sulfur-lithium ionic chains. Okay? And due to that, the solubility of Li2S2 in the solution is very low. But it's likely when you add salt, lithium TFSI salt to the system, things are going to change. And that's exactly what happened. So we added 1 molar LiTFSI into the same system, and we observed a significant change in the solvation structure. Well, we still observed a strong lithium and polysulfide interaction, but we noticed that now there is an increase in lithium solvent interaction. And that's coming because of the competing interaction from TFSI and polysulfide to bind with lithium. And this competing interaction disrupts this polymeric structure and allows more solvent molecule to bind with lithium, which increases the solubility of these lithium polysulfide species, Li2S2. However, like I mentioned, there are other lithium polysulfide species also present in the solution. So it's important to study what's happening with them. So we looked at the effect of polysulfide chain length. This is the exact same plot as I just showed in the previous slide. It's just a heat map of showing different peaks as a function of polysulfide chain length. And we found that these smaller order polysulfide species like S2, S3, and S4 have a strong tendency to form aggregates in the solution. And this tendency decreases as we increase the chain length of polysulfide. In particular, we found that S4 has 2 sharp peaks at very short distance, which suggests, and we found that we are forming this large polymeric structure of size almost 11 angstrom. And our experimental collaborators at Pacific Northwest National Lab used a PFG and MR to measure the hydrodynamic radius of different lithium polysulfide species. And they found that indeed for Li2S4, we are forming very large clusters. So why is that a problem? Because if your Li2S4 is one of the dominant species present in the solution, okay, and such large cluster formation can suddenly increase the viscosity of the solution, which can result in this sharp voltage decline, which is observed in the second phase of the discharge curve. Okay, so the solvation structure can significantly affect the dynamical properties. So the next step, we looked at the dynamical properties of lithium sulfur electrolytes. We considered 3 factors here: the effect of lithium TFSI concentration, the effect of lithium polysulfide chain length, and what happens when we mix these two. Okay, so for the first variable, we found that as we are increasing the salt concentration, we are going to decrease the mobility of different ionic species in the solution. And just to let you know, This plot shows the self-diffusion coefficient data of lithium TFSI, solvent, and polysulfide using experiments as well as simulations. Okay, so we found that as you're increasing the salt concentration, the mobility goes down, which is kind of expected, but we found that at particular 3 molar concentration, we are looking at almost a 2-order decrease in the mobility of ionic species in the solution. So if we keep on adding more salts, it's going to impact the mobility of ionic species, which can affect the conductivity of the ionic species. The second factor we looked at is the polysulfide chain length. And we found that as we increase the polysulfide chain length, there's a slight decrease in the diffusion of all the ionic species as well as solvents. And finally, when we add salt to the lithium polysulfide species, there's a further decrease in mobility of ions in the solution. We found a very interesting trend here for all the systems that we considered. And we noticed that for every system, the diffusion of the DOL solvent is higher than DME solvent. Okay, they both have very similar physical and chemical properties. They both have the same dielectric constant of approximately 7. But it was interesting to see that consistently one of the solvent is moving faster than the other. And we learned that that's happening because of preferential solvation of DME solvent over DOL molecule. And that's because of the geometry of DME molecule, which has the cyclic linear geometry, and it can bind through this oxys and atoms, compared to DOL molecule, which has the cyclic geometry, and doesn't bind that strongly with lithium ion. And because of that, DME molecules is kind of diffusing along with lithium ions, which makes its diffusion slower compared to DOL solvent. Okay, so the geometry of the solvent is also an important parameter to take into consideration. And as a natural step, we next studied the effect of solvent molecules on the structural and dynamical properties. And here we considered a system of Li2S2 with LiTFSI solvent. And we looked at the coordination number of lithium with the anions, as well as with the solvent molecule. The trends that we found here were very similar to what we observed before for magnesium salts. So we found that DMSO provides very strong, acetonitrile provides very weak solvation and results in formation of aggregates in the solution. Okay. On the other hand, DMSO provides very strong solvation to the cation by binding through its polarizable oxygen atom, and can separate lithium from both the TFSI anion as well as the polysulfide species. DOL DME has similar trends as of what we observed for acetonitrile. And glymes were again an interesting solvents because of their structure and their ability to wrap around the cation. They can dissociate the cation from the anions. And we observed the effect of this change in solvation structure on the dynamical properties. And there we found another parameter which plays a crucial role. And this parameter is the viscosity of the solvent molecules. So we found that the diffusion of ionic species is fastest in acetonitrile because it has very low viscosity. And it's second highest in DMSO. And now you should be asking me a question that the viscosity of DOL DME is actually lower than that of DMSO. Then why is the diffusion faster? That happens because DMSO is a very strong, provides very strong solvation and can dissociate lithium from the anions. And that's why the molecules are moving relatively independently in the solution compared to DOL DME and acetonitrile, where they're moving together in the solution. Okay, and that's why the mobility of ions in this DOL DME mixture is smaller. And for glymes, even though that also acts as a very strong solvent, it also has very, very high viscosity, because of which the mobility of the ionic species is the lowest in this tetraglyme solvent. Okay, so we identified these several different parameters, such as the geometry of the solvent, salt, as well as the viscosity, which is crucial in determining the structural and dynamical properties of lithium electrolytes. We also did one more work in which we tried to understand if at all we can control or manipulate the nucleation of lithium polysulfide species at the interface. And in this work, we considered the effect of donor number of solvents, and we considered three systems. And we found that as we are increasing the donor number of the solvent, we are increasing the lithium and solvent interaction. And that was a very monotonic trend. So the lowest donor number is for TMS solvent, the highest is for DMSO, and we observed a linear trend here. Okay. And we looked at the effect of this solvation structure on the nucleation of lithium polysulfide species, where we found that if the donor number is too low, like in the case of TMSO, then the solubility is very low, which results in precipitation of lithium polysulfide species at the electrode, which forms this insulating film-like structure, because of which the discharge capacity is very, very low. But if you're on the other spectrum of the donor number, such as in case of DMSO, the solubility is too high. If the solubility is too high, your nucleation overpotential is also very high, which results in formation of these small particles, and it results in slightly higher discharge capacity, but still very limited. And we found that for a combination of DOL-DME solvent, which has an intermediate donor number of 20, we are forming these large spherical particles, which forms an electron and lithium ion conducting network, because of which the discharge capacity is highest. And I would like to mention here that the nucleation process during the nucleation phenomena during electrochemical process is a very, very complicated phenomena. It involves a lot of different factors, which we did not include in this work. But even with the simplest model, this work shows that it is possible to alter or affect the nucleation pathways by changing the properties of by changing the solvation structure through changing the properties of solvent molecules. Okay. So for lithium sulfur batteries, we identified a lot of different descriptors, several parameters, such as the donor number and the geometry of the molecules and the viscosity of the solvent, which affects the structural and dynamical properties, which in turn affects the redox shuttle phenomenon. And some of the DFT results that I presented today are available on the Electrolyte Genome website. If you have never heard of it, I would suggest you go and check it out. We call it a Google search engine for electrolytes, where basically you can search for any molecule by any base molecule that you want. So let's say quinoxylene, which is a redox active molecule, and you will get result of all the molecules in the database. Okay. And you can select it based on the redox potential with the specific working electrode. You can export the entire database if you want and play around with it. You can add keywords, like you can include or exclude a specific element in your search, and you can see the results of the redox potential for that particular molecule. These are all optimized structures, so you can download these structures and do further calculations with these structures if you want. We added another cool feature to Electrolyte Genome website, which is called a substructure search. So oftentimes it happens, at least to me, that I see a nice molecule in a presentation and I'll forget its name, its chemical name. Then that's fine. You can just draw the molecule and you will get results of all the molecules in the database, which includes that base molecule. Okay, and again, you can include or exclude any element. You can play around with this different toolbars on the right-hand side to narrow down your search. Okay. So far, Electrolyte Genome has screened more than 30,000 molecules, so it's a pretty large database. So if you're interested in some electrolytes, this can be a good starting point for you. Okay, with this, I hope I was able to finish in time, and I would like to thank my current group and the people that I've worked in the past. I would also like to thank all the different computational resources from different national labs and universities, and all the experimental collaborators, including Professor Paul and Professor Mukherjee, for trusting computational people and working with us. Okay. And I would be happy to take any questions now.